things about chemistry where I say don't blame me. It's a convention that we're going to have to understand kind of the way chemists talk, actually the way scientists talk with regard to an atom. You guys would tell me that I have protons and neutrons, protons and neutrons, protons and neutrons, protons and neutrons. Wow, I got 1, 2, 3, 4. I got 4 protons in this nucleus. What element is that?
It's beryllium.
It is beryllium. And I'm going to go ahead and make it neutral. I'm going to put 4 electrons out here. Very good. And so some of you know those electrons will be kind of organized into shells and stuff like that. We'll be talking about that later. Yep, that is a beryllium atom. So in order to talk atoms, we know we need to talk about these 3 subatomic particles, and we need to be able to count them. So we have this thing called the atomic number. So, and sometimes I get this mixed up, but atomic number, and the variable we use is the letter Z. You're like, well, why don't you use an A? And I don't know. I think it's German. Atomic number, and that's the number of protons. So the atomic number for a beryllium atom is 4. Okay? So the next thing we need to count, oh, by the way, this says in italics here, and we'll be talking about ions just briefly coming up, I think, in the next part, but if your atom is what we see, nice and neutral, nice and balanced, electrically neutral, that means, like I've drawn it up here, you have the same number of protons and the same number of electrons outside the cloud as you have protons in it. Okay? So that's neutral. So if it's neutral, we have 4 protons. If it's neutral, we have 4 protons, 4 electrons. Okay? The next one, counting subatomic particles, is what we call the mass number. Sometimes students, for whatever reason, I don't know, and the variable for mass number is A. Do you get my problem here? I'm like, really? Why did you do that? Okay. So the variable for mass number is A, and we're counting particles, so it is an integer. I hope you guys, I'm not a math teacher, but an integer is a whole number. So we literally, for mass number, are counting the 2 subatomic particles that have mass. So it makes sense to me. So mass number is, like the slide says, the number of protons. I can move my electron here. Plus the number of neutrons. That's it. You got to count it. It's going to be an integer. Okay? Makes sense. Sometimes when I understand, because I think they got some bad advice in your upbringing of chemistry, but people want to use, let's pick on beryllium, want to use this 9.012182 as the mass number. And I'd be like, no, because that says you have a part of a proton or a part of a neutron. Mass numbers are integers or whole numbers, okay? We'll talk more about what that, how that number is related to mass number, although I usually don't kind of, it didn't go forward. Are you serious? Okay, mass number, there we go, sorry. Need that slide. So it's a variable A, it's another protons plus number of neutrons. Okay. All right, so the atomic number is the number of protons. When we're talking about subatomic particles, we talked about the protons and neutrons, electrons. We said it's the number of protons that give the identity to the element. And so, you know, like I said, if I draw a nucleus with 4 protons, you tell me that's beryllium. You know, 39 protons, you tell me that's yttrium. Okay, so it defines what an atom is. So atomic number is unique for a given element. Okay, so different elements have to have a different atomic numbers. So keep your eye on the ball. Atomic number, the variable Z, number of protons. Mass number, number of protons plus number of neutrons. They both weigh something. That's kind of why we call it the mass number. And it's a bit different here. So atoms of the same element can have different mass numbers. And what's varying then is this guy right here. You can have the same element, different number of neutrons, gives us a different mass number, but the same atomic number. Similarly, you can kind of have what I kind of think is overlap. It's possible to have like 2 different elements that have different number of protons, but their mass number is the same because they kind of make it up with neutrons. I kind of think neutron is Mother Nature's salt and pepper. 2 protons gives identity to the element. neutrons. We're going to see here in a minute, though, there are various forms, naturally occurring isotopic forms of the elements. If you look at a periodic table, well, I don't know, but iodine right here, like if you look at tin, antimony, tellurium, they get heavier and heavier. They have 118.7 AMUs is how much it weighs, 121.7 AMUs, 127.6 AMUs, and then, did I do that right? Yeah, I did that right. And then here, from tellurium to iodine, iodine gets a little bit lighter, 126.9 AMUs. But it has 53 protons versus 52 protons. Again, it's about Mother Nature. So all of this changing of neutrons gives us elements that have different, what we call isotopic forms. So atoms of the same element, of course with the same atomic number, different mass numbers, those are what we call isotopes of each other. So different mass numbers because they have different number of neutrons. So you definitely don't need to memorize this. This seems like one of those oxymoronic sort of phrases. Only one isotopic form seems silly to me, but these guys right here, aluminum, fluorine, beryllium, sodium, phosphorus, bless you, manganese, there's only one isotopic form that naturally occurs. Two isotopic forms, 3 or more isotopic forms. So there are times when, well, you've probably heard the word isotope here and there. For instance, like if you go get that test where they give you a barium dye, you swallow a pill or whatever, and then they take a picture of you, and it has flagged the structures that they're trying to look at. So they give you one isotopic form of barium that they're looking for. Okay. It doesn't. It is nasty, I think, what I heard. I've heard. Isotopes come into play when you're trying to do some sort of, like when we want to try to make sure all countries aren't necessarily engaging in fixing uranium so that they can go ahead and use it in military bombs and sort of like that. Uranium is one isotopic form, is nice and unstable, so you put it in a missile and you can make a nuclear bomb. So when we see countries that are concentrating using centrifuges, that particular form of uranium, we're concerned. That particular isotope of uranium. It's kind of rare, but they can they can use density to go ahead and concentrate. So the different isotopes do different things. Okay. So it's important here and there to be able to talk about the different isotopes of the elements. So I'm going to show you how we do that. So of course, carbon, the element carbon, we use the symbol C for carbon. Probably the most common isotopic form of carbon is carbon-12. Now, if we find carbon on the periodic table, you would find it right here, okay? And all carbon atoms have to have 6 protons in them, but this actually is the isotope that has a mass number of 12. So how many neutrons does it have? It has 6. 6 protons plus 6 neutrons gives it this mass number of 12. Perfect. So there's different ways we can do it. C12. Okay, we can go ahead and this is a convention that you're going to want to kind of become familiar with, where we have the symbol of the element, and then there on the left we've got 2 numbers. The number in the upper left-hand corner is the mass number. The number in the lower left-hand corner may or may not be there. That's the atomic number. To me, this is kind of redundant. If you have a periodic table handy, you can go ahead and knock that one out. But this is the mass number that can change. This is the atomic number. Yep. So again, the whole A and Z thing just drives me nuts. So whenever I get to this topic, I'm like, oh, I don't know. But A, what did I say? A is the mass number, protons plus neutrons, and Z is the atomic number. So somehow kind of get that into your box. Those numbers might be coming up again. So picking on boron actually, we would find it with a red 5 here. It's atomic number 5. Got a couple of versions. This is boron 10. This is boron 11. Of course, boron 11 has 1 more neutron than boron 10. So you might need to do something like this. So just shout it out. What do you think? How many protons does this fluorine have?
10.
Protons.
Oh, sorry. Protons is 9.
9. I'm liking 9. Very good. It's neutral, and I'll go ahead here in a minute and tell you what isn't neutral. But if it is neutral, and it is neutral because I don't see anything up here, how many electrons? 9. How many neutrons? 10. How'd you get it?
19 minus 19.
Yep. Yep. It's kind of fun to count those cute little particles. So that's what you did. Give them kind of that shorthand notation. Okay. So later on in the course, we'll be talking about the different types of compounds. There are ionic compounds and there are molecular compounds. And with regard to ionic compounds, you're going to get to learn how to name a few of them. Now, when it comes to ions, there are some ions that are just only one atom. We call them monoatomic ions. Okay. There are also, guess what, polyatomic ions. You've probably heard of things like nitrates, sulfates, phosphates. Those are polyatomic ions we'll be talking about later. But when just one little atom loses electrons or picks up electron, we call that a monoatomic ion. We'll be talking about, and you maybe already know this, it kind of depends on where an element is as to what sort of charge it will form. Actually, I'm looking close up at this particular periodic table, and I see +1s all over here. I see +2s all over here. I see -1s at least at the top here. I see -2s, and we'll talk more about that. But an ion just simply means it's not balanced. We have an unequal number of electrons as we do protons in the nucleus. Think of it this way, this took me a while. Protons are there to stay, they don't budge. What can budge in this atom are the electrons. They can come and go, okay? So if we get a few if at least one electron leaves, then we kind of, if we do the math, we have an extra positive charge. So we call that a cation. It's lost an electron or 2 or 3. And if we get an extra electron into the original electron cloud, then your atom is going to be negatively charged. We call that an anion. All right, I bring that up because now we should be able to kind of count particles just based, we'll talk more about ions later, but just based upon that little bit there. So I mentioned if you look in the upper right-hand corner, and if there isn't anything, it's neutral, like when we did fluorine a little bit ago. If there is something in the upper right-hand corner, that means that it's charged. It will either be a plus something or a minus something. A plus something if it's a cation, it's lost electrons. A minus something if it's an anion, it's gained electrons. All right, so here we go. I'm listing how many protons?
20.
20, yep, very good. Remember that atomic number may or may not be there for you. How many electrons is +2 charge?
18.
I heard an 18. I'm liking 18. How'd you get 18?
Subtract 2.
Yep. 20 protons, and the fact that it's got 2 less electrons, that's why it gave it a +2 charge. So 18, that's perfect. How many neutrons? 19. 19, how'd you get it? You subtract, yeah, from 39 you subtract 20. Very good. You guys got it? Ding, ding, ding. So 20 protons, 18 electrons, and 19 neutrons. Very good. And your homework I think it's kind of fun. Your homework will ask you to do things like that. Okay, let's do another one. What's Cl? What element is that? Chlorine. Very good. Okay, so how many protons? 17. Perfect. How many electrons? 18. How'd you get it? 17 plus 1. Very good. And by the way, this negative and -1, it means the same thing. Sometimes I'll put negative, sometimes I'll put -1. Very good. Got 18 electrons. How many neutrons? 19. Sometimes I do use a calculator. How'd you get 19? 36 minus 17. Very good. All right. Perfect. Okay. So we're on to the next part, but I've just gotten in the habit of trying to remind you that once we finish a part, I would hop, jump, skip out there and just knock those out of Alta. Okay, so you have kind of a couple of different Alta parts. Part of your Part 8 homework is due The 12th, that's tomorrow, isn't it? Okay. And then part is due Monday. So it's Thursdays and Mondays. Okay, on part 9. We might even get past where my husband's at in his class. We'll see. If I talk too fast, let me know. I'm not doing it on purpose. Okay. So average atomic weight. There's a mouthful there. How much basically does an atom weigh on average? So I think I probably already mentioned this before. In most periodic tables, in that black and white periodic table I gave you that you'll have for your test, that doesn't have the names, for every element, you have the symbol of the element, and you have 2 numbers. You have a whole number, and you have a decimal number. That decimal number is the average atomic weight. Synonyms for average atomic weight are average atomic mass. This is a good one down here. We're going to kind of talk about why those decimal numbers are what we call a weighted average. The units for how much an atom weighs, we're going to use AMUs, or atomic mass units. All right. So we've talked in here how you always have to have some sort of standard. And actually we pick on the element carbon, not just any elements, but one isotopic form of carbon, carbon 12, mass number 12. And by definition, if you have, is it 1 mole? Oh, if you have 1 carbon atom, it will weigh exactly 12.00 AMUs. A few slides ago, we talked about, when we talked about subatomic particles, we said approximate mass of a proton and a neutron is approximately equal to 1 AMU. I was doing your ALTA homework for this time, just kind of seeing what it looked like, this part. And a neutron weighs just a little bit more than a proton. I was also doing your ALTA homework. And there are some things I think is really cool for you to know, but you might need to look up. One of the things I don't cover is that actually it is so cool. And since I just read it on ALTA, I'll tell you how this works. So if I were, for this beryllium atom, to take the individual masses of the 4 protons plus the 4 neutrons, okay, plus the 4 electrons, it would weigh just a little bit less than it. How do I say it? The individual masses don't add up to the mass of the single beryllium atom. It is so cool. That mass actually is converted into energy that atom uses to hold together. And it's called binding energy. So if you see that on your binding energy. And it's actually the nuclear force, the strong nuclear force that keeps the nucleus together. I think that's so cool. Where was I? Oh, yeah. Okay, so average atomic weight. So they actually are units of AMUs, atomic mass units. Sometimes you'll see, instead of the word AMU, it will be U. So I think AMUs, atomic mass units, we always have to have units, no naked numbers. That's the same thing, it's just the letter U in some cases, so kind of keep that in mind. Of these equivalency statements, I usually put an arrow for things you need to memorize. Of these equivalent statements, I probably would memorize the second one, just for kicks. We're actually going to definitely be talking more about the value that you see over there, the 6.022 times 10 to the 23rd. Some of you guys already know that that's Avogadro's number. So that's one you probably have somewhere. If you don't have it, you will. And so 1 gram is approximately equal to 6.022 times 10 to the 23rd AMUs. If you memorize that, you can go ahead and if you look at the relationship of the previous equivalency statement, that actually is the inverse of the number 6.022 times 10 to the 23rd. So if you got the second one, you really already have the first one. Okay. So I'm going to talk you through a classic type of problem. You can roll your eyes, classic type of problem. And it is where we come up with these average atomic weights. For instance, the beryllium, that 9.012182. How in the heck do you come up with that as the weight of a beryllium atom? Atomic mass units. And in order to do that, we're going to have to, and I don't know if beryllium is a good example, but we're going to have to go out into Mother Nature and find out for each for each element of interest where we want to calculate an average atomic weight, we have to know what sort of isotopes there are out there. What sort of isotopes do we have? Not only what sort of isotopes do we have, but how much of that isotopic form is there? I'll show you how that comes into creating what we call a weighted average. Okay? So this percent abundance means some scientist has dedicated their lives to going out, taking a representative sample of a particular element in nature. And this whole idea of getting a representative sample, that's a science in and of itself. And then basically has assayed that sample to find out how many atoms of a particular element there is. So they get how many there is there for that isotope divided by the total number of all isotopes. So it's a ratio. And take it times 100% and they get percent abundance. So for instance, copper has two common isotopic forms. Notice we've talked about this sort of convention where we have the symbol of the element Cu in the upper left-hand corner, we have the mass number. So we have copper 63 and copper 65. If there's only two isotopic forms, what should their percent abundances add up to be? Okay, what do these add up to be? 100%. Yep. It's just saying, in other words, if you were to go out and painstakingly obtain representative 10,000 copper atoms, 6,909 of them would be isotope copper 63, and 3,091 of them would be the other isotope, copper 65. Okay. So this is just kind of some information about different elements. So hydrogen, the simplest of elements, atomic number 1. So actually, I have 3 isotopic forms listed up here. But if you look at the legend there, regular old hydrogen, its abundance is 99.985. Regular old hydrogen has a mass number of 1. The mass number is the number of protons plus neutrons. How many neutrons does hydrogen 1 have? Yep, I think I heard it, 0. Just 1 proton. When we get into talking about acids and bases, we're actually going to say if you have a hydrogen ion that's lost its electron, guess what? It's just a proton floating around in there. I think that is so cool. Most hydrogen is just the normal hydrogen. For whatever reason, hydrogen is so important, they get fancy names for the other 2 isotopic forms. We have D stands for deuterium, T stands for tritium. There is a little bit of deuterium that naturally occurs, but tritium is not so much, right? Then another one I have up there is boron. We kind of looked at boron 10, boron 11, neon 2 isotopic forms, and magnesium 3 isotopic forms. Now, if you want to jot down www.ptable.com, because I'm going to go out to the internet and show you how cool I think that is. Oh no, I know. Don't worry, I got this. How many people in here? And I got to come up with an extra credit pot because sometimes I've given extra credit here and there. Like on your phones, like you have like a chemistry, a periodic table, interactive periodic table on your phone. Everybody needs one. They're free. So I'll come up with a column for extra credit and do something with it. So if you do extra problems. But anyway, this ptable.com, I think it might be www, although it doesn't look like ptable.com. It's great. It works on the PC. One of the things I want to show you is across the top there, you can see the different, where's my cursor? There it is. Across the top here, you can see the different things you can click on. I'm going to go to isotopes. And of course, the way this works is the way you probably think it works. If I click on copper here, it's going to go ahead and give me 2. I have my copper 63. You can kind of see up there, it's a relative abundance, 69.17. And here's my copper 65. That's what we've been talking about. This third down here is just the copper itself. So anyway, there is that. just to kind of show you, I was playing around with this. How cool is this? You click on compounds and say you want to know compounds, compounds that have carbon and hydrogen. You can pick up carbon and you can kind of see it added right over here. You see some carbon containing compounds, but you say, well, I want the ones that have carbon and hydrogen in it. Now I have carbon and hydrogen. Now these aren't all the compounds, but I just think it's so cool. And you're like, okay, I want to add oxygen. You know, maybe it's just me, but I think that's so fun. They're all clickable. And we're actually, if I click over here for orbitals, one of the things we're going to talk about is how electrons are arranged. Again, some of you are kind of already familiar with this, but this tells you how the electrons are arranged. Just think that is so fun. Too bad you can't use this on a test, right? Okay. So back to OpenStax. I guess this isn't OpenStax, but this is just to kind of give you a visualization. We have fluorine, chlorine, magnesium, and lead going across from left to right. And you can see, I like lead. Isn't that fun? So you see actually it has 4 naturally occurring isotopes. That yellow there is trying to represent in relative abundance of 1.4%. And we've been talking about, if we stay with lead, you can see that that is lead with a mass number of 204. You can kind of see the relative abundances of each of the other 3 isotopic forms of lead. So I told you the classic problem where you're given a particular element, you're given isotopic or abundance information about the isotopic forms of that element, and you're supposed to knock out the decimal number, the average atomic weight. I'll tell you that this is one of those problems that you can actually look at the periodic table to check it. Okay, so there is that. So who knows what this little looks like an E thing is?
Oh, gosh dang it.
It's the Greek letter starts with an S.
Sigma.
Sigma, very good. And the mathematical operation also starts with an S. So what does that mean? What does that big sigma mean? Actually, we saw it in the standard relative deviations we did the other day. What did you do with your individual deviations? You added them up. So it's the Greek letter sigma, and it means summation. So what it means is for every isotopic form, we are going to take how much it weighs, the weight of that isotope, times its, not its percent abundance, but its fractional abundance. I'll show you how to get fractional abundance, percent abundance. You just divide by 100. And we're going to add them all up. So it kind of ends up kind of looking like this. Okay? So we would do, if we had one isotopic form, our first isotopic form, we would say how much does it weigh times its fractional abundance plus the next one, how much does the next isotope weigh times its fractional abundance plus you get it the third, the fourth, etc. For however many isotopic forms we have. Okay, so someone's going to have to give you how much an atom of that particular isotopic form weighs and its relative abundance. So yeah, we're usually given fractional abundance, but you can see that in that formula I gave you, we're going to be multiplying by, we're given percent abundance, but we want to use fractional abundance. So all we're going to do, you're going to see me take my percent abundance, and to get it parts per 1, I'm going to divide by 100 basically. It's easier to show you than to tell you, right? So we're going to pick on copper, and I can tell you already, we're after, this one says 63.546. That's our target. But by golly, if you just have a problem, you will have a problem on the test. If you just go to your periodic table and write down that number, I'll think you're clever, but I will laugh. You have to show your work is my point, that you know what you're trying to get to. Now, as we do this, can you see where copper 63 is more abundant? So if we apply that formula, what you're going to see is that actually this mass is going to be weighted more because it's more abundant. That's just how it works. So let's see how we do this. So the first term will be associated with the first isotope. So we'll take how much that isotope weighed, 62.930 AMUs. And then to get from percent abundance to fractional abundance, we'll take that 69.09%, and we'll take that 69.09 and divide it by 100. Plus, and we're only going to need two terms because there's only two isotopic forms. For the other isotope, it weighs 64.928 AMUs, and its percent abundance is 39.91%. To get it to fractional abundance, we just divide by 100. Slap that in your calculator. I know I've been all about rounding, carefully rounding, but here's where I guess almost do a Hail Mary. And I have a slide coming up somewhere that basically says if you have a relatively heavy, if you have an element that's heavier than 10 AMUs, give yourself 2 decimals. So if we give ourselves 2 decimals, you're looking at 63.55. Now, sometimes I will do an average atomic weight problem like this, and it will not match up with my periodic table. It'll be off a little bit. And honestly, I think that's a case of they have revisited their percents, their percent abundances, have come up with different numbers, and so anyway. Okay, so just to kind of visualize what we just did with copper. The first copper was much more, it's copper 63, much more abundant than copper 65. So if we were to do a simple average, and honestly, I see this a lot on tests. Don't make this you on a test. A simple average would have been where you take the mass of one, the mass of the other, since you have 2, you add them together, and you divide by 2. You can't do that because one's a lot more abundant. You have to apply the approach that we did. Okay, so applying the approach that we did makes it the final average atomic weight much closer to the one that was more abundant. Okay, hydrogen, oh my goodness, don't get me started. The decimal number for hydrogen is 1.008. It's one, and we use a lot of hydrogen in this class, so 1.008 AMUs is an average atomic weight. It has 2 naturally occurring isotopic forms. This one was a lot more abundant. A simple average, if you take about 1 for the most abundant isotopic form, plus about 2 for that deuterium, you get 3. 3 divided by 2, a simple average gives you 1.5 AMUs. But this one's so much more abundant that actually, that's why we're at 1.008 AMUs for the weighted average. Okay, oops. Well, I don't have to say when these are due, but this, remember? Yeah, thank you. This one's due Monday. And it's only because I can. I did the Alta one, and the Alta one for part 9, I still want you to do, but it throws in kind of even more of a twist than my simple one, so just do that's what these are like undersized. That's it for now, guys. See if cut up with my friend.
So there's the same question.
It's the same question. I asked her about it.
What's that?
I'm having a couple of questions.